Hello, today we're going to talk about reactivity 3.2.1 and 3.2.2. It all has to do with oxidation and reduction, and there are different definitions for oxidation and reduction. We're also going to relate it to half equations and balancing redox reactions. So what are oxidation and reduction? One way that you can define them is in terms of electrons. So when something gains an electron, that's reduction, which is kind of weird. Then when something loses an electron, that's oxidation. I use the acronym oil rig, where oxidation is losing. So oxidation is losing electrons, and then reduction is gaining electrons. But I've also seen Leo the lion says grr, losing electrons, oxidation, gaining electrons, reduction, whatever works for you. But you can also define oxidation and reduction in terms of hydrogen. So if something is gaining hydrogen, that's reduction. But if something is losing hydrogens, that's oxidation. And for the most part, we're going to talk about the gaining or losing of hydrogens in reference to organic molecules being oxidized or reduced. For the most part, if it's not an organic molecule, then we're more going to use like just proton chemistry for that, which would be in reactivity 1, which would be acid-base reactions. But for this unit, for organic molecules, we can talk about the gaining of hydrogens being a reduction reaction or the losing of hydrogens being an oxidation. We can also use oxidation numbers to help us track the ability to gain or lose electrons. And let's just take a quick second to review some of those oxidation number rules. An element by itself in its standard state has an oxidation number of 0. A monatomic ion has the same oxidation number as the charge. Hydrogen in a compound has an oxidation state of +1, with the exception of metal hydrides, where it's -1. Oxygen in a compound is -2, with the exception of peroxides, where it's -1. And then everything else you're going to add up to the charge on the compound. So let's look at a couple examples of these things. If I have something in its standard state, like oxygen gas, which is O2, its oxidation state is 0. Whereas if I have something like, let's say I have calcium chloride, that consists of 2 ions, calcium, which has a 2+ charge, and chloride, 2 chlorides, which have -1 charges. So their oxidation states are +2 and -1, respectively. Now, if you have something like hydrogen in a compound like H2SO3, that hydrogen has an oxidation state of +1. Or if you have oxygen in a compound, the oxygen would have an oxidation state here of -2 in that compound. Now, if you have another example where you need them to add up, let's use this H2SO3 and work through that. The overall charge on that compound is 0, so all of the oxidation numbers on that compound have to add up to 0. Hydrogen, we just said, was +1, and oxygen in a compound is -2. There are 2 hydrogens, so that's a +2 total, and 3 oxygens, so -6. The sulfur has to be something that'll make the whole total add up to 0, so the sulfur must be +4. So anything that doesn't fall into one of the other rules, you can figure out by using, making sure they all add up to the charge on the compound. Now, why is this useful? Well, we can use the oxidation numbers to track whether something is gaining or losing electrons. So let's say, let me take this calcium chloride example. If I have calcium and chlorine gas forming calcium chloride ions, the calcium by itself is in its standard state at 0. Cl2 is its standard state at 0. And then in the compound here, we found out their oxidation states are +2 and -1. Since the calcium, its oxidation number is going up, it was oxidized. The chlorine was going from 0 down to -1, so it was reduced. And I find that one is a little easier to remember. If the oxidation number is going down, it's being reduced. If it's going up, it's being oxidized. Now we can also define redox reactions in terms of oxidizing and reducing agents. So let me write out an example. So let's say I have something like zinc plus hydrochloric acid forming hydrogen gas and zinc chloride. You can still use oxidation numbers to track what's being oxidized and reduced. So the zinc is going from 0 to a +2. Hydrogen is going from +1 on the compound to 0. And the chlorine is staying at -1. So the chlorine was neither oxidized nor reduced. Since the zinc is increasing, it was oxidized. The hydrogen goes down, so it was reduced. Now, whatever is oxidized, we can also call that the reducing agent, because it needs to be there to cause the hydrogen to be reduced. So the zinc is acting as the reducing agent. The hydrogen ions are also acting as the oxidizing agent. That's because the hydrogens need to be there in order for the zinc to be oxidized. So the hydrogens are acting as the oxidizing agent. So whatever is oxidized is also called the reducing agent. Whatever is reduced is also called the oxidizing agent. So we define a redox reaction as a reaction where there is a change in oxidation number or where there is a transfer of electrons. So that example that we used in the last one with the hydrochloric acid and the zinc, this one is a redox reaction because you can see that there are oxidation numbers changing from reactants to products. Let's look at another example. If I have something like this, you can assign oxidation states to all of the things there. Monatomic ions are the same as their charge. Hydrogens in molecular compounds are +1, and oxygen in compounds are -2. So I've assigned oxidation states to all of the atoms there. Then you need to see if anything is changing. Sodium's the same, oxygen's the same, hydrogen is the same, and chlorine is the same. So since there's no changes at all, this one is not a redox reaction. So one thing that we can do to help track oxidation and reduction separately is write half equations. Half equations just show what's happening to half of the substances in the reaction effectively. So let's say I have something like, if I go back to that zinc example, if I write this separately and show that the zinc chloride is separating, I can show that the zinc is forming zinc 2+ ions. And then if I do the same thing with the hydrogen, the HCl, strong acid. The hydrogen ions are forming hydrogen gas. You also need to keep track of electrons. There are 2 electrons being lost from the zinc because that's oxidation, and there are 2 electrons being gained by the hydrogen because it's being reduced. So these are called half reactions. They have to show the electrons involved. This is the oxidation half reaction, and this is the reduction half reaction. Sometimes they will give you the half reactions. So let's say I have something like calcium, forming calcium ions and 2 electrons. And then I have, let's say I have phosphorus gaining 3 electrons, like this. I can use those half reactions. This one is oxidation, this one is reduction. But I can use them to write the overall reaction. You just have to make sure the electrons match. I can tell this one is oxidation really easily because the electrons are being released on the product side, and this one is reduction because the electrons are being gained into the reaction. So I have 2 electrons and 3 electrons. I need to make them the same. I can multiply this whole thing by 3, multiply this whole thing by 2, so I have 6 electrons total. Then I can combine all of the reactants on one side. So 3 calciums plus 2 phosphoruses plus 6 electrons. And the product side, I've got 3 calcium ions, 6 electrons, and 2 phosphorus ions. Well, then the electrons are the same on both sides, so I can ignore those. So my final overall reaction is the 3 calcium atoms plus 2 phosphorus atoms yields 3 calcium ions plus 2 phosphorus ions, phosphides. There is another method that we can use for this. I guess it's not a different method, it becomes a little bit more involved when you have more complicated compounds. So let's say I have something like C2H5OH reacting with the dichromate ion, and it will form carbon dioxide and chromium ions. You might be asked to balance this in an acidic solution. And it becomes pretty difficult to balance because of the oxygens and hydrogens. There's a method that we can use to solve this simply. The first thing you want to do is separate it into 2 half reactions. So notice that this has the carbon, so we're going to group it with the other carbon compound, C2H5OH. And then we're going to do the chromium compounds together. The next thing you have to do is balance the atoms that are not hydrogen or oxygen. So I have 2 carbons on this side. I need to make it so there's 2 carbons on the product side as well. There are 2 chromiums on the reactant side, so I need 2 chromiums on the product side. Once I get all of the other atoms balanced, then I can go in and balance oxygen. And I do that by adding water molecules. So there's 1 oxygen on the reactant side versus 4 on the product side. I need 3 additional water molecules on the reactant side. For our other half reaction, I have 7 oxygen atoms. That means I need to add 7 water molecules on the product side. So that's how you do oxygen. The next step is to balance the hydrogens using hydrogen ions. Because it's an acidic solution, you're going to assume that you've got excess hydrogen ions. So on the reactant side here, I have 6 plus 6, that's 12 hydrogens. So I'm going to add in 12 hydrogen ions on the product side. On the other half reaction, I have 14 hydrogens. So I'm going to add in 14 hydrogen ions on the reactant side. Now that I have all of my atoms balanced, I also need to balance the charge using electrons. So for this first half reaction, the charge on the reactant side is 0. Nothing there has a charge. But on the product side, I have a positive 12 charge. I can add in 12 electrons to make this go down to 0. And now you have the same charge on both sides. So I added in 12 electrons there. For the other half reaction, on this side, I have a positive 12 charge, 14 from the hydrogen, and negative 2 from the dichromate. And on my product side, I have a positive 6 charge from the 2 chromium ions. I need to make them equal, so I can add 6 electrons. Squeeze it in here. Because if I add in 6 negatives, that will get it down to +6, and they will be the same. Okay, so now my electrons are balanced as well, or my charges are balanced. The next step would be to make sure that both half reactions have the same number of electrons. This one has 12 electrons, this one has 6. So I need to multiply everything here by 2. So I'm going to have 2 of the dichromates, 4 of the chromium ions, 28 of the hydrogens, 12 electrons, and 14 water molecules. So now my electrons are the same. Finally, I can now put all of the reactants on one side. So C2H5OH, 3 waters, 2 dichromates, 28 hydrogens, and 12 electrons. And then on the product side, I have 2 carbon dioxides, 12 electrons, 12 hydrogens, 4 chromium ions, and 14 water molecules. Then you need to cross out anything that is the same on both sides. The 12 electrons will cancel, and the electrons will always cancel because you intentionally made them the same. Water molecules, 3 of them cancel out, 3 here, so this 14 goes down to 11. And then 12 of the hydrogen ions cancel. So this goes down to 16. So my final reaction is the C2H5OH plus 2 dichromates plus 16 hydrogen ions yields 2 carbon dioxides plus 4 chromium ions plus 11 water molecules. And so that's how you balance it. I intentionally picked a long and involved one to show you all of the possibilities. Sometimes you'll only need to do some of the steps to get it to work, but that's how you use the half reaction method. Now the last part of this section is about redox titrations. So titrations, remember, is where you slowly add one reactant into the other reactant until it reaches an equivalence point where you have the equal number of moles of both. And that will give you some information about concentration, usually. You can do a titration with a redox reaction. You just need to be careful with the mole ratios. So let's, if I have 1.50 moles of my C2H5OH, I can use the mole ratio, the 1:2 ratio there, to find out how many of the dichromate ions will be reacting to reach equivalence point. And you can, of course, use grams or volume considerations when you're doing these calculations as well. But the biggest part is being careful with the mole ratio and making sure that your reaction is balanced. Another thing I want to point out is sometimes that you guys are probably used to using indicators for titrations, which change color at different pHs. Redox titrations very frequently will have their own color changes involved. So like the dichromate ion is going to have a different color than the chromium ion in solution. And so you'll be able to observe that color change without having to use a separate indicator. So let's look at a couple examples. Oxidation states to the metal ion in the following. These are complex ions, remember, and the ammonia has a 0 charge. It's neutral overall, so that +2 charge comes only from the copper. And because that copper is a monatomic ion, its oxidation state will be the same as the charge, so +2. In our second example here, the ammonia is neutral, but the chlorine is -1. And so if I have a +1 overall and -2 from the chlorine, that means the chromium must be +3 to get that to add up appropriately. Now for this example, it's asking which species is oxidized and reduced, and then label the oxidizing and reducing agents. The easiest way is to use oxidation numbers. Elements by themselves are 0. A hydrogen in a compound is +1. The oxygen in a compound is -2. So it's -1. Oxygen is -2. This chlorine, in order to get this to work out properly, becomes a +1. So this one's kind of interesting because you notice the chlorine is going from 0 to -1, which was reduced. But the chlorine was also going from 0 to +1, which was oxidized. So the chlorine is acting as both the oxidizing and the reducing agent, which is interesting. Now in this example, we want to name the compound with the lead and the 2 oxygens. Using IUPAC rules, I need to figure out the charge on the lead, the oxidation state of the lead. So since oxygen is -2, the lead must be +4. So your name will be lead 4 oxide. Okay, so now we need to balance the reaction for NO3- and copper reacting in acidic solution to produce NO and Cu2+. I'm going to write as two half reactions first. Then I need to balance any atoms that are not oxygen and hydrogen, which they're already balanced. I have the same number on both sides. Then I balance oxygens using water. I need 2 water molecules on this side, and the other half reaction is good. Then I balance hydrogen using hydrogen ions. I need 4 hydrogen ions on this side. And so that's balanced now. The last step is to balance the charge using electrons. I need 3 electrons over here, because the -1 from the nitrate and the 4 positives from the hydrogen. And in this one, I need 2 electrons on the product side. Then you need to make the electrons the same. So I'm going to multiply this one by 2 and multiply this one by 3. And I'm going to go ahead and combine all of the reactants together at the same time. So 2 nitrates plus 8 hydrogens plus 6 electrons plus 3 coppers yields 2 NO plus 4 water plus 3 copper ions plus 6 electrons. And then you can cancel out anything that's the same on both sides. The only thing that cancels out here is the 6 electrons. And remember, the electrons will always cancel. And so there is my overall equation. So this links to structure 3.1. What are the advantages and limitations of using oxidation states to track redox changes? It's very useful when you're doing a redox reaction where there's definitely an electron transfer. Because losing electrons is oxidation, gaining electrons is reduction. But we can also define reduction and oxidation in terms of their hydrogens. If it's gaining hydrogens, it's reduction. If it's losing hydrogens, it's oxidation. So that would be a limitation, is that it doesn't necessarily help you with those organic oxidation and reduction reactions. Okay, so then the surface oxidation of metals is known as corrosion. Sometimes we can call that rusting. What are some of the consequences of this process? So if you have something like iron undergoing corrosion, it produces rust, which is Fe2O3, which can become very brittle. It's an ionic compound. It can dissolve the metal, basically, and reduce the structural integrity of your metal object. But sometimes, depending on the compound, it can create a layer that is oxidized on the top that serves as a protective barrier from the solid metal underneath. So if the surface layer is corroded, oxidized, then the metal underneath cannot be oxidized any further, and it becomes very strong that way. Finally, why are some redox titrations described as self-indicating? A lot of times when we're doing redox titrations, we're using ions that are colorful. Typically, they'll have transition metals in them. And when they are changing oxidation state, they are changing color very frequently. And so when that reaction has reached equivalence point, we can see a very distinct color change happening. So that acts as an indicator. We don't need to use any outside indicator for that.